All right, everyone. We had a number of questions for homework last night on page 453. Any issues with questions 1 and 2, 5 to 9, 11, or 13 to 16 on page 453? All right, 2, 6, and 7 it is. Number 2 says, just a short qualitative question, says, explain why momentum is a vector quantity. Sometimes we see a question where it's so straightforward, we actually don't, we think that it can't be that straightforward. Okay? We think there's got to be more to it. There's not for this question. Okay? Why is momentum a vector quantity? Why is it a vector quantity? Well, it's simply because it's dependent upon velocity. Right? It's dependent upon velocity, and velocity is a vector. Direction matters for velocity. So direction has to matter for momentum as well. That's it. That's all there is to it. If it depends on velocity, and velocity is a vector, then momentum's got to be a vector as well. 6 says provide 3 examples of situations in which velocity is the dominant factor affecting the momentum of an object. Sometimes we're reading a question and we don't miss the question. We don't get the question wrong because we don't know the physics. Sometimes we're reading a question and we get the question wrong because we can't read the question. Sometimes we see a word that we don't understand. Here's what dominant means. You know what dominant means there? What does dominant mean there, Mason? I think you were kind of nodding your head there, weren't you? Yeah. Okay. So, okay, power above something else. Okay. A situation in which velocity is above any other factor in determining the momentum. Okay, the dominant factor, the prime factor, the most important factor, above something else. Okay, any of those things work there. Give me a situation where velocity is the most important factor or the factor that's above all the other factors there. Perfect. Okay, that's the one that the typical one that we get here. The bullet leaving the gun. Bullet's going pretty fast, right? 4, 5, 600 meters per second, maybe twice the speed of sound, but it's pretty light. It's got a lot of momentum though. It can do a lot of damage because it has a lot of velocity. Give me another one. Somebody in the last class said an arrow, with a bow and arrow. Guys, listen, if you think about this for about a minute, you could think of 100 examples. Because all we're looking for here is something that's moving. Got to be moving, otherwise it has no momentum, right? But something that's light. Something that's moving fast. Doesn't have to be light, but it's got to be moving fast. If it's moving fast, then velocity is the dominant factor, or the prime factor, or the main factor in its momentum. Yep. Concorde, yeah. Concorde they don't fly the Concorde anymore, but when the Concorde flew, its momentum was due to mass and velocity, but it was most known for its velocity, right? So certainly that would have been a big factor. I don't know necessarily about the most dominant factor, because the Concorde was heavy, really heavy as well. But it certainly would have been a major factor in the momentum of it. What about the mass? When is the mass the most dominant factor? A train is a perfect example of that, right? Even a train going really, really, really slow. We define momentum as product of mass and velocity, but we think of it as how hard it is to stop something. Right? How hard it is to stop something. Train's going down the track really slow, Mason, going down the track really slow, but you're not going to stand in front of that train, put your hands out and try to stop that train, even if it's going slow, because that train is hard to stop. It's got a lot of momentum, even though it's going slow. Its high amount of momentum is due almost entirely to its mass in that case. Anything else that's heavy? If it's moving and it's heavy, then mass is the dominant factor in its momentum. Okay, a train, a semi-truck, anything, an asteroid, a meteor, okay, anything that has a lot of mass and is moving. All right, finally, question number 7. Love this question. A Mexican jumping bean moves because an insect larva inside the shell wiggles. Would it increase the motion to have the mass of the insect bigger Or would it increase the motion to have the mass of the shell bigger? So you got this shell, you got this little insect inside it. The insect is wiggling around. I don't really know how to draw a wiggling insect, so that's what that means. Those little lines around it mean the insect is wiggling. Would it increase the motion of the shell to have this insect heavy or to have this shell heavy? Who says insect? Who says shell? Okay. Anybody want to volunteer why they said insect? Okay, so that seems to make sense, right? Heavy shell, you want to move something that's light, right? Not something that's heavy. Okay, that seems to make sense. Have you said shell? You got a reason? Oh, okay, because it has more of a mass, it's going to have more momentum. Okay, okay, both of those seem like they're good, right? There's a flaw with one of them, obviously. Okay, but both of them seem on the surface to be good explanations. The answer is the insect. Here's why. It's effectively what you said, Parker, okay? But we're going to talk about it in terms of momentum. The insect has a lot of mass. It's got more momentum. Now, you got a lot of momentum now. You're transferring it to a shell. You want that shell to be light, okay? Because more momentum will cause a light shell to move faster versus a heavy shell to move faster. Now, the flaw in your argument there, Abby, was you said you want the shell to be heavy. That's going to give you more momentum, right? Well, no. It gets a certain amount of momentum. Let's say it gets 10 units of momentum from the insect. More mass isn't going to give it more momentum because it only had 10 to get from the insect. So you don't want more mass in the shell. You want less mass, right? Here's the thing. Listen to this. If you want the shell to move fast, do you want A, lots of momentum transferred to something that's light, or do you want a little bit of momentum transferred to something that's heavy? Okay, you want lots of momentum transferred to something that's light. Does that make sense? All right, so the answer is insect, okay, lots of momentum being transferred to something that's light. Right? Okay, guys. For the last couple of days, we've talked about momentum, and we've talked about it quite a bit. We said that momentum exists at a specific moment in time. At a moment in time. Momentum at a moment in time. We don't talk about the average momentum. We don't talk about the change in momentum in terms of just straight P is equal to M times V at least. How do we quantify, though, when the momentum is changing? How do we quantify when a car is speeding up and its momentum is changing? Without saying, okay, here's the final momentum, or here's the initial momentum. How do we quantify the interval of the momentum changing there, the car speeding up? Well, now we're going to introduce this concept called impulse. Impulse is defined quite simply as the change in the momentum. So it would be final momentum minus initial momentum, right? Whatever the car has at the end of the speeding up phase compared to what it had at the beginning. Whatever the rock has as it's hitting the ground versus whatever the rock had when it was at the top of the cliff. Impulse is the change in momentum. Not average, okay, not medium, mean, whatever. It's the change in the momentum. The final minus the initial. It's a vector. Because if momentum is a vector, and impulse is the change in momentum, then impulse has to be a vector as well. Now we're going to derive an equation here, but before we do that, I want to ask you a question. Joey's desk up here is at rest. It has zero momentum. I want to change its momentum. I want to give his desk an impulse, a change in momentum. Do you understand the context of the question here? Okay, we don't know what the question is yet, but we have a context. I want to give Joey's desk an impulse. I want to change its momentum. It has no momentum right now. how am I going to give it momentum? How am I going to provide an impulse for Joey's desk? What do I have to do to it? Don't make this question harder than it has to be. If I want Joey's desk to have momentum and it doesn't have any right now, what do I got to do, John? I got to apply a force. Okay? So I apply a force of 10 newtons. Desk moves. Got momentum, right? It had an impulse, a change in momentum. Make sense? Now, if I apply that force, what did I say, 5 newtons? 10 newtons? Okay, so I apply that force of 10 newtons. Is there any way that I can increase its momentum even more without changing my force? Kyle, was your hand up there? No? Yeah, let's not talk about that right now, but okay, let's apply the same amount of force for a longer period of time. So instead of applying 10 newtons for a half a second, let's apply 10 newtons for 5 seconds. It's going to go way faster if I do that, right? And the longer I apply the force, the faster it's going to go. So 2 factors that are going to influence the change in the momentum here, the impulse here. That's going to be the force and how long I apply that force for. The force and the time. Let's derive an equation now and see how that relates to what we just figured out. Newton's second law says F is equal to m times A. Okay, physics 20, right? You may not have remembered the difference between the first law and the second law, but everybody remembers F equals m times A. I'm going to do a replacement here, a substitution. Tell me if this is legal. Tell me if I'm allowed to do this. F is equal to m times A. F is equal to m times delta V over delta T. Is that okay? Can I do that? Is that mathematically sound? Sure it is. Sure it is. Let's rearrange this just a little bit here. Let's take the T up by multiplying. I get F times T is equal to m times delta V. That's just rearranging. That's just algebra, so that's okay. Take a step back for a sec. What's the equation for momentum again? Mark, what's the equation for momentum? Good. P equals m times v. And strictly speaking, you're right? You said momentum is equal to mass times velocity. We talked about that yesterday, right? It's really not mv. It's really mass times velocity. But we represented m times v. So we're going to say, again, the equation is m times v. I see an equation up here that has m times delta v in there. If momentum is mv, then what do you think m delta v equals? The change in momentum. What did we define the change in momentum as? What did we call the change in momentum? Impulse. So we're saying that m times delta v is the impulse. Look what else is equal to impulse. F delta t. What 2 factors influence the amount of impulse that something would experience? The force and how long you applied the force for. So in other words, if you're ever asked to solve for impulse, you're going to either multiply m times the change in velocity, or you're going to multiply the force times the time. Now, I'd like you to take a look at your data sheet for a second. I'd like you to find that equation, please, on your data sheet if you can. Who's found it? Okay, Kristen, what do you notice about that equation on your data sheet versus the equation that I have up on the board there right now? Anything different about it? No? Okay, so on your data sheet, it just says F times delta T is equal to m times delta V. It doesn't mean what we've written down here is wrong. It isn't. It just means that your data sheet isn't telling you everything. If you're ever asked to solve for impulse, go to that equation, F times delta T is equal to m times delta V. But you have to recognize what it means. Most times they tell us V equals d over t. Velocity equals d over t. Here they don't. Here they're just expecting us to know that impulse equals F times t. And impulse equals m times delta v. They don't tell me that that's impulse, but that's what it is. So don't get bogged down with that. Just remember that this equation is the equation for impulse. Now, when you're asked to, when we did momentum, just straight momentum P equals m times v, there was really only one situation that we were going to use that for to solve a problem. And it was pretty straightforward. When you were asked for momentum, you used P equals m times v. Maybe you were asked for the momentum of the car traveling down the road. Maybe you were asked for the momentum of the rock as it struck the ground after falling off a cliff. Maybe you were asked for the momentum of a fly as it moved through the air. But every time you needed to use that equation, you were asked for momentum. Impulse is a little bit trickier. There's three situations in which we're going to use impulse. When do we want to think impulse? When do we want to use impulse to solve a problem? Well, the first one's pretty obvious. If you're asked for impulse, okay, that's about as easy as solving for momentum. If you're asked for impulse, then set impulse equal to F times T or M times delta V. If you're asked for. It goes for everything in physics 20 and physics 30, right? If you're asked for it, use the equation that has that variable in it that you're asked for. The second situation, when we have a change in momentum. Maybe the question says, when the car came to a crashing stop when it hit the concrete wall, what was the change in momentum of the car? All right, use impulse. Maybe the question says, when the bug hit the windshield of the semi-truck, what was the change in momentum of the bug? Okay, all right, use impulse. Change in momentum. Maybe the question said, as the baseball player threw the baseball, what was the change in momentum of the baseball? All right, use impulse. Ask you for change in momentum. Maybe it said, as the basketball player caught the basketball, how much momentum did the basketball lose? That's a change in momentum, right? Momentum lost. Yeah, that's a change in momentum. That's an impulse problem. Whenever you've got a question that asks you for the change in momentum or the momentum gained or the momentum lost, that's impulse. Finally, the third one, and this is the trickiest one. When you have a force and a time in the same question. This is the tricky one because that question probably won't even mention the word impulse, or for that matter, probably won't even mention the word momentum. A 1,500 kilogram car is traveling down the road at 100 kilometers per hour. It comes to a crashing stop in a time of 0.25 seconds. What's the force of impact on the car? I didn't mention the word momentum. I didn't mention the word impulse, but I did mention force and I did mention time. That's an impulse problem. That's the hardest one to recognize because we're looking for those words, momentum and impulse, but we don't see it. But we do see two other words, force and time. We see those, think impulse. Okay. Here's an example that's on page 458 of your textbook. It says, to improve the safety of motorists, modern cars are built so that front end crumples upon impact. Do you guys know that? Do you guys know that cars are supposed to crumple? Cars are supposed to get destroyed. We want them to get destroyed. If you're in a car crash, you want your car to get written off. 30 years ago, they built cars so that that didn't happen. 30 years ago, they were much more rigid. 30 years ago, a car could survive a crash easier than a car can now. It was a lot cheaper to repair them. So why have they changed that? Have they changed that because they want you to wreck your car and go buy a new car? They changed that because it's safer when the car is destroyed. Because if the car is not destroyed, it's going to be you that gets destroyed. It's you or the car. It's you or the car. 30 years ago, it was you. Now it's the car that we sacrifice, not you. So we have these crumple zones. A 1,200 kilogram car traveling at a velocity of 8 meters per second to the east hits an immovable wall and comes to a complete stop in 0.25 seconds. Hey, what's that variable there? V. V what? VI. It's the initial velocity. Anything else we have there if we Read between the lines. What is it? Let's do a stop. VF would be 0, right? What's the impulse provided to the car? All right. I told you a minute ago, if you're asked for impulse, use impulse. What's the average net force exerted on the car? And C, for the same impulse, what's the average force? Oh, we're changing the time in C, so we'll kind of make that separate problem. We'll worry about that later on. Let's do A and B right now. I want to find the impulse. Well, we know that impulse is equal to F times T, but it's also equal to M times delta V. Which part are you going to use, FT or MV? FT? Sure, it's perfectly valid. Perfectly valid. Okay, let's go ahead and try to use F times T. What's F? Oh, we don't know. What's T? Yeah, we know T, but we don't know F. So it's F times 0.25 seconds. That doesn't seem to help us too much, does it? Listen, the reason I wrote that down is because I want to make a point with that. Okay, somebody says, let's use F times T. The point that I want to make is that that's a valid equation. Go ahead and try. The worst that's going to happen is it's not going to work for you. You're not going to get the wrong answer using a valid equation. Go ahead and try it. If it doesn't work, then try something else. Okay, that didn't work. So now let's try M times delta V. We got M, it's 1,200 kilograms. Delta V is 0 minus 8. Right, final minus initial. That works out to be negative 9.6 times 10 to the 3 kilograms meters per second. Anybody tell me why that's a negative value? Don't say, oh, because 0 minus 8 is negative 8. Like, not mathematically why it's a negative value, but conceptually, why should it be a negative value, Andy? Good. There's two ways to think of this. One, because you're losing momentum. It's a loss of momentum, a drop in momentum, negative impulse. Second way, its momentum was to the right. The impulse that it experiences is to the left. Look, impulse is in the same direction as force, right? Which way does the force have to be to stop this car? To the left. So impulse has got to be to the left as well. So, Andy, you're right. It's a drop in momentum, but we can also think of it as, oh, force has to be to the left, so impulse is to the left as well. Okay, let's look at B. What's the average net force exerted on the car? Hey, look what I see. Force and time. We already solved for impulse, so let's use that value that we just solved for. And now let's set it equal to F times T. Let's rearrange this to solve for F. T goes down by dividing. I think that works out to be 3.84 times 10 to the 3 newtons. It's a pretty big force. Pretty big force. That's what I see, though. For the same impulse, Joey, go ahead. Should be negative. Did I make it positive? Yes. Should be negative. You're right. Thank you. And of course, if it's moving to the right, how are you going to stop it? Apply a force to the left. For the same impulse, what would be the average net force? Wait a second. For the same impulse, can we do that? Yeah, let's think about that for a second. This car, forget about the wall for a second. Okay, forget about the wall. I'm telling you, we got a car that has a mass of 1,200 kilograms. It's going at 8 meters per second. And I'm going to tell you it stops. I'm not going to tell you how it stops. Maybe it crashes into a wall with a crumple zone. Maybe it crashes into a wall with a rigid bumper. Maybe it comes to a gradual stop at a stop sign. I don't know how it stops. The car had 9,600 kilograms meters per second of momentum. Now it's got none. Its impulse is negative 9,600 no matter how it stops. It doesn't matter whether it comes to a crashing stop here or whether it comes to a gradual stop at a stop sign, the impulse will be the same. Impulse doesn't hurt you. Force hurts you. The impulse of the car will be the same no matter how it stops. Let's figure out what the force is, though, with the rigid bumper. F is equal to delta P over delta T. The impulse is still 9.6, negative 9.6 times 10 to the 3, because it's going to be the same no matter what. But the time here is 0.040 seconds. We do that math, and I think we end up with negative 2.4 times 10 to the 5 newtons. What do you notice about those two forces? They're different. Which one's bigger? Which force is bigger? Second one. Which time is bigger? Okay, so when the car stops quicker, the force is, no. Okay, the second one, the force stops quicker, right? The force is more. When the car stops quicker, the force is more. That's why we want the crumple zone to increase the amount of time that it takes the car to stop. That's going to decrease the force. Not going to do anything to the impulse, but it's going to decrease the force. And remember, it's the force that hurts you. That's why we have an airbag in a car. Your head's going to come to a stop no matter what. You're in a crash, comes to a stop. Maybe it hits a steering wheel, maybe it hits an airbag. The impulse is the same. But the airbag spreads it out over a bigger time, which decreases the force. That's why when you catch a baseball, you don't just catch a baseball like this. Stick your hand out and not cradle it a little bit, right? You move it, you might not even think of it. Basketball, the same thing, right? You don't even think of it. But you know intuitively to kind of bring your hand back a little bit, right? What does that do? Increases the stopping time of the baseball or the basketball, decreases the force. That's why a goalie wears goalie pads. Okay, when I think I was about 12 years old, playing in a rink in my side yard, had a neighbor across the street shooting pucks at me. I was playing goalie. I didn't have goalie pads. I had shin pads. I said, I was pretty cocky. I said, take a slap shot. I had a baseball glove. I had a hockey glove, no helmet, shin pads. Take a slap shot at me. So he takes a slap shot at me. I go down, the top of the shin pad, okay, that covers the knee, flaps out, and the puck hits me right in the knee on a slap shot. It hurt a lot. But if I was wearing goalie pads, it wouldn't hurt. Why? Because the goalie pads increase the time that it takes to stop that puck, which decreases the force. Does that make sense? You have a question, Matt? Sorry, what's that? Sorry, you're right. Made a mistake there. Still works out to be a bigger force, just not as much bigger as I said. 3.84 times 10 to the 4. Oh, for B. Okay. So did I have that one right? Okay. Negative 2.4 times 10 to the 4. Oh, 10 to the 5. Oh, and this was 3.84 times 10 to the 4. Okay. 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 Thank you. So it wasn't as big of a mistake as I thought I made there, but still a mistake. The irony is it was a small mistake. I just made a big mistake out of it. Right? Good at that? Okay. Here's your homework for tonight. 2 questions. That's it. You're also going to have, for Friday, worksheet number 2. Now, there's 9 questions on worksheet number 2. We only know how to do 8 of them at this point. It's not homework for tomorrow, but it will be homework the entire thing for Friday. So if you got some time, and you only got 2 questions here, if you got some extra time tonight, maybe take a look at worksheet number 2 so that you have less to do tomorrow night.